Okay, so I think we're going to get started with our first keynote address. As Mike mentioned earlier this morning, we've had a little bit of a reshuffling in the keynotes due to transportation and medical challenges on the part of other keynote speakers. And we're fortunate to have Scott Bortoff, who's willing to jump in and then move up his keynote talk from yesterday to today. And so I'd be glad to welcome him and introduce him to this talk. I've been working with Scott for a number of years at Mitsubishi Electric Research Labs. Scott originally actually graduated from University of Illinois and was a professor at University of Toronto for 10 years, and then moved into industry where he worked at United Technologies for almost 10 years and has been at MERL for longer than that. Scott's focus really is a lot of system level design, a lot of focus on control, both for thermofluid, HVAC type systems, which we'll talk about today, and mechatronic systems, robotic systems. He has a lot of experience working with Modelica for probably 20 years now, which is something that a few people in this room can say, although not that many in general can say that. But a lot of experience. Yeah, it's all Hubertus's fault. So with that, I'd like to turn the time over to Scott. Again, looking forward to his remarks. And at the end, for those of you who are virtual, well, if you can post your questions in the chat, either towards the end, I'll try to make sure that we can ask those questions of Scott at the end of this talk. So with that, I'll turn the time over to Scott. Thank you.
So thank you, Chris. It is indeed a pleasure to be here live. I think I completely agree with what Mike Tiller said this morning. I think this is a great format, doing it hybrid, but it's so much better to see everybody's face. Now, with that said, I beg your forgiveness because this is, I think, only the second time I've stood up in front of any people since 2019, because, of course, all of these things have been remote. And in fact, I gave a talk at our company, Mitsubishi Electric, in Japan 3 weeks ago, and it was in an auditorium, smaller, and nobody showed up because the 31 people who did show up were all virtual. So that was okay because I didn't have to wear my mask. I thought I would talk about something that a lot of you are interested in, I hope most of you, and that is buildings and HVAC and the subject of sustainability. And that's a big subject, and I think a very motivating subject for me personally and many of you. My company, I'm proud to say, I think is also, trying to do its best to reduce its impact on the climate. And sometimes I'm very optimistic. So on the left there, on your left, is a building that Mitsubishi Electric built in Ofuna, Japan, that actually is zero energy building. And I'll tell you about that. But on the right there is the thermostat in my hotel room here in Dallas, Texas, which I woke up this morning, it was a little cold, and I thought I would just bump it up 2 degrees, and what happened? The heat came in. So we have some work to do. I thought I would do really 2 things today, maybe. First of all, I'll give you a little bit of a peek under the kimono, so to speak, about what we do at MERL. I work at a company's research lab, and we publish our work mostly, but a lot of what we do is for the company and is somewhat proprietary. And so it's a bit of a mix. But I think it's important at these types of events to kind of share what we try to do, because we in fact use a lot of the tools that some of you around the room make. And you don't always hear about how much we use them and how much we appreciate them. You tend to hear when our air model isn't quite compatible with your air model and can you fix it. So I'll talk a little bit about what we do and what are our research challenges. And I especially want to look forward. So as Chris said, I've been sort of using Modelica in one form or another for a long time. Hubertus taught me 20 some odd years ago. And it's a terrific tool. And I think it is both a great platform as a software platform and also as a community where we can make a serious dent. What is it called? Okay. On some of these big important problems. And I want to talk about what I see are opportunities for research. And one of my objectives in doing this is I think that it's important to align in some sense incentives. I think a lot about this. Of course, academics have certain incentives to do research, government labs, the kind of lab I'm in, industry, we all have different incentives for doing things. When these things are aligned, we can actually accomplish quite a lot. And when they're not aligned, then it seems like a lot of our work is, we wonder, is it for naught? And the other thing I really do like about this community is that it is not as siloed as some of the other research communities I'm a member of. I think it's incredibly important to be broad and to get out of your silo and to work in areas that are perhaps not your PhD area to solve some of these problems. So my little counterexample about incentives is, of course, there's a lot of government incentives to put heat pumps on buildings, and so what happens? Heat pumps get slapped all over buildings because the various parties are incentivized to do exactly that, and the result is not what you want. So I kind of want to get into building HVAC, talk about what I see are challenges at the equipment level, at the system level, and especially, I think, have some conversation about what we might call a service level of this fun subject called digital twin. So Mitsubishi Electric is a big company. We make air conditioning systems and a lot of other things, and that's probably all you need to know there. But this is kind of fun. A few years ago, the company decided that they wanted to build a zero energy building. This is on the campus of one of the 2 research labs in Japan. It's in Ofuna. And during the COVID times, it was actually accomplished. This is the first building that was government certified as zero energy in Japan while it was under construction. It's a 4-floor, medium-sized office building. It's full of all kinds of fun HVAC equipment. So it's a kind of it's a candy store for Hong Tao and Chris and I. Some interesting power systems, a lot of interest and prototypes in terms of DC in the building. And in its first over a year of operation, it actually did better than net zero. So it actually generated more electricity than it consumed, which is actually pretty astonishing. It's amazingly instrumented building. The architecture is beautiful in terms of its energy performance, perhaps not aesthetics. And the equipment is quite stunning. So this is a building that we get to play in, and is reason for me to be optimistic that some of these problems that we face can be addressed. So the HVAC business is, for a lot of people, something you don't really think about every day. It is actually a very interesting business. It's very, very profitable right now. And it is driven by a lot of trends. As you may know, the fluorine gases that are used as refrigerants are basically getting phased out in Europe over the years. And so you can sell less and less of these in terms of their greenhouse gas potential per year. And that puts a lot of pressure on us as a company to adopt new refrigerants. And eventually they will be entirely phased out. And so, as they are with most cars these days, the greenhouse gas potential in those refrigerants is close to 1. And that will come, but that's a challenge. There are a lot of new testing standards. Of course, the big push is what we call electrification. So getting rid of appliances that burn gas to make heat in your buildings and installing heat pumps, which is great for our business, but a real challenge in many ways. So there are, of course, new building performance standards, and the ASHRAE standards continue to improve, although I would argue kind of slowly. So it's actually quite a dynamic business, and that has a lot of implications on the product we make, and that has implications on how we design them and how we control them. And so what we see over the years, the diagram there, is a very simple vapor compression cycle. It's the sort of simplest diagram that we can make, but these things can get quite complex with many, many heat exchangers in the inside of the building and on the outside of the building, and lots of compressors and a whole lot of valves. That thing on the lower left there is what we call a hybrid branch controller, which is essentially a rat's nest of valves and heat exchangers and wires and things. But the trends are basically more variable actuation, more compressor speed, variable compressor speed, variable valve settings. 30, 40 years ago, everything was on-off with on-off valves, and there was no control. Today, everything's variable speed, variable valves, variable fan speeds, and probably the more important trend is that we want to operate these things over much wider operating ranges than we ever did. So if you bought a system today, it might go from, sort of 25 hertz, the compressor speed, to 120. And we'd like to run those way down, almost to zero, for very low ambient heat, and much, much higher for places like Texas, where we are, where it gets very hot in the summer. And so because of that larger envelope, and because we would like to sell more heat pumps, and it's probably a good thing in climates like Minnesota or northern Sweden or wherever, there are basically just much, much larger operating envelopes. There's also a lot more integration, which is one of these words that is overused both vertically and horizontally. What I mean by that here is that the equipment that we build in a factory actually has a lot of the building control features built right into it. So, you might, traditionally think, oh, there's sort of a building management system at the top and system level controls. There's a nice hierarchy, but that's getting actually very blended through the use of these VRF systems that my company makes, are becoming more popular. So at the same time, we have very limited measurements, which makes my job, which is mostly control, always a challenge. And so, when you look at these things as dynamical systems, which is what they are, much more multivariable, much more interacting, much more coupled, nonlinear, which is a term I don't like because it tells you what they're not. But essentially, the loop gain changes over different points in the operating envelope. And the other sort of feature of all these systems is they're really dominated by constraints. There are a lot of operating constraints, limits, maximums, minimums, that need to be enforced in order for the equipment to work properly. And so this has a lot of implications on what we do. It used to be that control in this field was just basically software that turned something on and off. And now it's, I would argue, probably the hardest part of designing one of these systems. So I'm going to tell you a little bit about what we do at MERL. Some of these might look a little strange, but we have a kind of strategy. We try to emphasize the mathematics of model-based design at MERL. And what that means, actually just look up the definition. And so one of my features, perhaps we'll say, is I'm a little bit anal about defining terms. And a lot of the terms we like to throw around, like model-based design, the meanings have been watered down over the years. But this is actually very well defined to be a mathematical method of designing complex systems. And of course, we use models and tools and simulations to do that on the left. And we like to talk a lot about that at these types of conferences. But really, it's how we use those that's important. The methods, the mathematical methods, primarily. And of course, there are always computation in some form. But there's math that needs to be understood underneath it. And we tend to focus on that at MERL. Primarily because that should be our role in the company. And then, of course, you need to have some kind of process. We're not as involved with process because we're not part of the business. But I would say that, just sort of looking at one of these design Ds does not define model-based design. There's a lot of know-how in terms of the methods, and we try to develop and use new methods. And if you look at kind of what we do every day, so the word strategy to me means what activities we do. It's a verb. It's very action-oriented. Every day that fit together in order to accomplish a goal. And essentially, we build models. We make libraries. And over the year, especially Hong-Tao and Chris have probably 20, 30 person years of investment in building models. And we use other open source models, of course. But you can't do that in a vacuum. And the other part of that is the problems that we solve. And those are not always public. So, a lot of those problems are designing new types of controllers for new products or fixing controllers for old products. And these two things fit together. So the aspect of designing control or an estimation or doing some kind of dynamic analysis provides requirements to models, and the models allow us to solve those problems. And over the years, as I said, it's been 13 years we've been at this, we build up this immense library of knowledge and models. And that's a very important part of our strategy. I think that's a great thing about Modelica. It's so well structured and organized that you can accrue these large libraries over time. And eventually, you win. You have so much knowledge and so much modeling libraries that this just has to get used everywhere. We do a lot of experiments at MERL, but very specific transient types of experiments, and we try to use math. We try not to sort of hack solutions. That's an important theme because I think we tend to think about models as sort of hidden math. We put it in equations and then put it in an object and you run a simulation. But actually, we really need to access that mathematics in order to solve some of these problems. And that gets to what we'll talk about in a little while. We have a very Modelica-based control design process. We start with some requirements. We build a bunch of models. Everybody knows how that works. One of the most important aspects of all the tools that we have is we can compute very reliably linearizations of those models and very robustly. And those linearizations are really the core piece of information you need in order to do good design for these types of systems, these multivariable, highly interactive systems where we need robustness. And we do all of that design work using MATLAB, but using the mathematics of multivariable control and robust control and nonlinear control. We often get asked, what should we use, Modelica or Simulink? And it's a sort of I hate that question because you should use both, and we use both. And what you see here is we actually use Modelica a lot more than probably anybody else. Because as soon as we have the control designed in MATLAB, we go and pull it back into Modelica and we recode it more or less. And when I say the control, I mean all the linear, the whole thing, the startup sequence, all of the logic, because the libraries and the basic model of computation in Modelica is extremely well suited to that purpose. And it's really not in MATLAB Simulink. Of course, we do a lot of analog and then digital simulation. And then the one thing that's I like a lot is that we can just unplug the model and plug it into our experiment, over the network, and run essentially the same exact controller recompiled to do an experiment. So there's no recoding, absolutely no recoding. Recoding is a nightmare. And over the years, we've gotten smart about not increasing the number of tools we use, but getting rid of the number of tools we use. And then, of course, at some point, you need to generate code for a product. That's something that we're just starting to do. The new EFMI tools and standard is something that's very important to us, and we're starting to work on that a little bit. Not a lot of progress to report, but that is definitely our path forward. So I'll skip this. I think the one thing I like to tell people is Modelica is great. We all do modeling and simulation, but just the fact that I can compute a linearization of these incredibly complex models. And when I say a linearization, we compute a lot of them. Reliably is, I would argue, just as important. Because without that, you can't do this rigorous design. And you're basically, not applying the formal methods of math that we learned in control theory in the last 100 years. And you're doing sort of a guess and check. And that, it just doesn't really cut it anymore for these systems. At the end of the day, we end up with some sort of typical closed loop feedback. We use a lot of the properties and object-oriented features of the language, both for the physics and for the control system. Because the control system tends to have certain structure. You don't want to have to redo that structure. So we'll realize the controller as, say, fully analog to do fast simulations, and then just replace all the PI blocks and other blocks with digital versions of those, and you don't have to recode the thing. You just recompile, and it's don't make a mistake. I think for me, these ideas of object-oriented modeling and not having to recode, people tend to think, well, from one project to the next project to the next project. But I think about this as when we're in one project, I've designed this very complicated controller, and I don't have to redo the structure. It evolves with the product development. These are typically what controllers look like. One person might, well, this is just a bunch of PIs, and that's exactly right. It's a bunch of PIs, but there's like 10 PIs all connected together to enforce 20 constraints and about 100 parameters to do all that. And so it's very complex, and so you can see you don't want to have to recode any of this. You just want to replace that one block with a discrete time block, and you're good to go. And this is very simplified, I have to say. So one thing we do, I'll just share this with you. you think, oh, you just compute one linearization, you do one design, you move on, you write your paper. Actually, for any sort of given product, for any design, we have to compute, hundreds to thousands of linearizations because these operating envelopes are very big. So the outdoor air temperature varies, and the indoor air temperature varies, and the humidity varies, and you have to cover that whole space. And so automating this is absolutely vital. When I started working on this, Chris would send me a model by email. I would spend a day or two doing the design, and I would send him back the PI parameters. Now, there's too much. So we have to automate a lot of this, and I can't even do that in a day anymore. The automation aspect of doing this in Dymola is, we have to use Dymola because of the thermal fluid properties is absolutely vital. These systems are very stiff, incredibly stiff. So a lot of our models have time constants from a millisecond to a megasecond. So that's like 10 orders of magnitude, which is absurd. So the millisecond comes from the small heat exchanger volumes, and the megasecond comes from, one of Michael Wetter's big models in the buildings library. Not quite a megasecond, but it's a lot. It's about a day or two. And if you look at the spectrum, it's very uniformly distributed in the center there. And if you look at the Hankel singular values, they always have this nice property of sort of a nice uniform distribution. The good news is that linear algebra is so robust these days that we can linearize these pretty reliably, although there's some tricks that I can't talk about entirely, but and you can reduce them pretty reliably too, even for these very, very large and very ill-conditioned models. So that's good. I guess I'll show you this. One of the fun things about these labs, this probably won't show very well, is so this is an infrared camera taking a picture of an indoor heat exchanger during a transient. And so the purple color is colder, that's the liquid refrigerant, and the warmer color is darker, the orange color is warmer superheated refrigerant. And the thing about this video you see is it's not stable. So the boiling action inside these things is like a percolation in your coffee maker. And that can cause interesting problems for us. The things that look like veins on this are thermopiles, sorry, that we use to take a lot of measurements. And so even though all of our models appear to be stable, in fact, the dynamics are stable but have interesting nonlinear dynamical response that is sometimes important. Let me show you something else that's kind of a pain, but also interesting. One of the things that we're interested in doing is reducing the amount of refrigerant in these things for obvious reasons, because we can only use so much and it's bad for the environment. So a lot of the refrigerant ends up subcooled in the condenser, most of it. And if you can reduce that, that's terrific. So we started looking at controlling what's called the subcooling, which is the amount of temperature difference between the condensing temperature and the liquid that comes out the other side. And one of the things that happens when you're operating this is essentially the gain changes, the sign of the feedback changes in certain conditions. And so we tend to mount sensors on the heat exchanger like these little diamonds here. And when there's a transient, like you turn the fan on, the point at which the condensing takes place, just as you saw in that previous video, will change. And if it moves past that first sensor, suddenly the feedback gain changes sign, and every controller will go unstable in that condition. And we see this in the lab. That's what that middle plot is there. And this is something that we actually didn't think about too much when we were doing theoretical control design. And then you get in the lab and sometimes something just goes unstable and it takes all day. You can see it takes about half an hour there. And then you figure out what's going on, which is why the experiments are important. So these things are a pain to control because. So just another thing, we don't, again, like I say, the reason I'm showing you some of these things is because we're a little bit of an opaque place. We don't publish everything we do. But this FMI and FMU standard is incredibly important for us. And the reason it's important is because we can now, Modelica is a complicated language. People in our factories are not going to be using Modelica. Okay, it's just, I have a hard time with it. Chris has it. He's pretty good. Bortoff's pretty good. But the FMI allows us to put an Excel spreadsheet interface to that. And once you do that, nobody cares about Dymola anymore. They just care about an Excel spreadsheet. And this is immensely valuable. And so, you know, I do want to say the people that develop this and maintain this and are advancing this is really, really important. The solvers maybe could get a little better, but this is something that we use a lot. So, so while I'm talking about equipment, I thought sort of last little subject I want to talk about is there's a lot of interest because of these things have so many constraints, and we're interested in energy optimal control that model predictive control makes a lot of sense. And there are a lot of papers on this, both at the equipment level and the building level. It's a subject that a lot of people are interested in. And so we started looking at this, and we have a pretty strong group in model predictive control at MERL for other reasons. Probably the first time we tried this for a decent sized system, what happened, we sort of did all this design, and tune it all up, and you go in the lab and it goes unstable. And so that was a bad day. It's like, but it went unstable in a very interesting way, because anything, sometimes you get these sort of oscillations 180 degrees out of phase. What you have is some kind of robustness problem. And it's some kind of feedback loop that is got too much, you know, you've lost margin. And the reason, of course, this happens is because the conventional MPC is not based on any robust control theory whatsoever. It's based on LQR and LQG. Most people don't think about, you know, state estimators being that important. And so you just plug in, you know, identity matrix gains, and it goes unstable. And, you know, the reason is, it's one of my favorite papers. You know, John Doyle wrote this paper in 1978 with the best abstract ever. You know, what are the guaranteed margins for LQG regulators? There are none. And he's John, so he got away with that, and it's true. And this is exactly what's going on here. And so we figured out how to essentially redesign the gains using H-infinity control theory, and then realize that as an MPC. And I think this is important. This is applying mathematics that is very robust, you know, to these problems. So model predictive control is a great idea, but I also see, you know, you have to pay attention to, you know, these sort of stability margin issues. So I won't go through all this. There's a paper on this. There's a very complicated feedback diagram here. But by applying a little bit of mathematics, we reduce the number of parameters we have to tune to something like 12. And the rest of it is all synthesis. And all of those 12 parameters have physical meaning. And that's really important for us. It's really important for our company. As you can imagine, there are a lot of parameters that need to be tuned. And if you can reduce or eliminate them, and by the way, make the thing more robust, you win. So we figured out kind of how to do that. And lo and behold, you know, you get really nice performance. And these are experiments done using that same process I showed you earlier. You take exactly the same model you're running in simulation, and you plug it into the experiment. And it really does work the first time, maybe the third time, because the first two times something, you know, goes wrong in the lab. But so, you know, it enforces constraints. It's optimal in a certain energy sense, and it's very robust in terms of its feedback gain. This was a couple years ago, you know, and then our lab closed. I don't think we've turned the thing on since, because we've been away, you know, for lockdown and things. But, you know, another kind of message here is that we have to constantly keep working on these problems. You know, I think, you know, when I was in graduate school, you worked on a problem until you had a paper done, and then that was it. You kind of go on, you work on the next problem, or, you know, you do a grant until it's done, and then you do the next grant. And usually those things are not sustained long enough to have a significant impact. So we started this work probably 2016, probably before that. And now we have it just barely running for kind of a linear model. But really we have to add a lot of things to this, the sort of non-linearity of the system, and how to turn it on and off, and how to figure out how to run an MPC in a little cheap embedded processor that costs less than, you know, a few bucks, 50 bucks, something like that. These are hard problems, so you have to stay at it. And, you know, I think eventually we will see an MPC controller in some of these products, but it will be near the end of my next 23 years. So I wanted to talk about what I think are research problems. That's kind of what we do at MERL from kind of a high level. But I think what I see is the most important problem for equipment in buildings is robust operation. These things, and you know, even some of the products that we've sold don't always behave stably. And If they did, they would operate much more energy efficiently. And at this level, at the equipment level, really all you care about is energy efficiency. That can be well defined. At a building level, honestly, energy efficiency cannot really be well defined. Some of you might argue with me, but thermodynamically, I don't really know how to do that. But at the equipment level, it can be, and the goal just needs to be to get it to operate robustly and energy efficiently over these very, very large ranges. And that's a really hard problem. The automotive industry went through a lot of these challenges when, emission controls were introduced, and 30 or 40 years later, you have incredibly efficient and clean gasoline engines and other types of engines. And I think this industry is sort of just starting to get into it. Of course, the other goal is to reduce the refrigerant charge. And that also introduces lots of challenges to operation and control. These systems are increasingly what are called, perhaps best called, multi-mode. I should have written multi-mode systems. Systems whose, so in Modelica speak, it means the number of equations or the number of variables changes depending on what mode it's running in. So if I turn off an indoor unit, I don't really want to simulate that anymore. It's kind of foolish, right? So how do I code that? And this turns out to be a very difficult mathematical problem into Modelica so that I don't have to simulate the same number of equations for always. And these systems are very, I use the word hybrid, but hybrid means too many other things, so multi-modes are better. There's a lot of on-off, there are a lot of modes of operation. All of these things run in heating mode or cooling mode, so they change directions. They go into defrost, they're off, and we want to be able to simulate not just in one of those modes, but how they switch among all those different modes. And that's a really hard problem. It's a hard problem from a software point of view, and it's a hard problem from a mathematical point of view. And so if you're looking for a good research topic, boy, that's a great one. I kind of wish I could go back to grad school and go attack that one, but maybe someday. The other one is an old one, but I think the subject of nonlinear model reduction, which has received a lot of attention, but I don't believe it's all that relevant in my honest opinion, needs to be addressed. So these models are very, very stiff and they have very broad time constants. And so we should be able to do some kind of singular perturbation type of analysis, but I would like it done symbolically. So I can sort of control and understand which equations and where the timescales separate, and not have a black box, a neural net model or something like that. I think it's much more valuable to retain the mathematical structure, and that's a very hard problem. And it would be valuable to do it using software because all our models are encoded in software. You can't write this stuff down anymore, of course. So again, it's more than just sort of one PhD thesis problem, but I would really encourage people who have that inclination in terms of mathematics and computer science to attack that one. And then, of course, model predictive control at this level, because that's a subject that's almost of separate interest. So I think the main research problem there is to make it robust. And robust in the sense of what a feedback loop means to be robust. So we're talking about margins. At the beginning I talked, maybe I didn't talk, but I had the word up there about silos. And my field controls become very siloed. So when I was a graduate student, I think I got a degree in control. But now you get a degree in nonlinear hybrid MPC. And the word hybrid and the word robust means something completely different, which is astonishing to me. So when I talk about robustness here to that group, they don't understand, which is a strange thing. But I think robustness in this sense, it needs to be further researched and developed. And then this whole idea of mode switching and gain scheduling and how to handle all the nonlinearities and embed this stuff. These are very open research problems. So I want to switch to a different topic and then I'll be done. So I have maybe 20 minutes. So if we think about HVAC systems, I think of this in terms of, there's sort of an equipment level and manufacturers are largely involved in that. And then we have building level. This is a bigger mess. You have people who build buildings and own buildings and use buildings, and there's obviously dynamic interaction between the two. And then we might imagine, and you know, my company, many companies have been thinking, gee, we need to get into the solutions business. We need to get into the service business. And you know, what does that mean? These are more undefined terms. But I think finally, at least for me, the idea of a digital twin of both buildings and in the thermodynamic sense of that, and HVAC equipment makes some sense. So again, the people who work with me are sort of cringing now because I'm very anal about defining things. And so, you know, I think we started talking about this 10 years ago, at least 7, about digital twin for this subject. And you know, what is it? What do we mean? And so then you start digging at the literature a little bit, and you find that, well, you know, the kind of person who coined the term thought that this was some kind of modeling artifact, right? And that artifact software would include things like behavior and bill of materials. And the key idea was it would follow a product through its life cycle. And that's a good idea. I like that definition. But then what happened was, over the years, the word got used to mean lots of different things. So now does it mean just a simulation model? I really don't know. But so then I say, well, we have to define it. And so my definition is essentially a virtual or a computer simulation model, like a Modelica model, which is appropriate for thermodynamics, say, of some product that is used in real-time operation. It follows a product through its life cycle, and it has to make use of some kind of real-time data to do that. So it's running real-time. And, you know, I think this is not a new idea, right? NASA was doing this, you know, when I was a small child, and obviously weather forecasting is a very good example of this. But I think it's, you know, been kind of overhyped a little bit. Anyway, that's not that important. For us, though, we see kind of 2 distinct opportunities here. And I do believe they are distinct. And one of them is we could imagine a kind of a digital twin or a real-time model of a piece of equipment that we sell. And that equipment might be very large for a building like this, or it might be very small for the little apartment that I live in. But it's basically taking the real-time measurements, perhaps not running a model real-time, but collecting those and then storing and simulating a model in order to, and this is important, what's its purpose? In order to predict something that's valuable, okay? And the things we see that are valuable pieces of information are the refrigerant charge in that piece of equipment, and perhaps even where that refrigerant charge is, and the heat flux flowing through certain heat exchangers. So we can do something really cool in a building like this. We can actually heat this room and cool the room over there. And if you can estimate how much heat's flowing through each one, then you can charge each customer for that. So I can charge to cool your room and heat your room. And there are lots of building owners who want that. But we can't do it accurately to meter standards today. So we're working on that. And of course, estimating the charge has been it's a hard problem. And this is, I think, a good example of, you know, I said earlier, you know, where do you have alignment between sort of objectives or intentions? And, you know, my company would like to make money selling a solution, right? We'd like to sell you the information about how much charge is in your HVAC. But a lot of companies and a lot of building owners would like to know if their HVAC stuff is leaking. And so there's alignment there. And so we're trying to make some progress on this on sort of on the left side for equipment. And then on a building level, I really do think this is a completely different problem. It's a much bigger problem. It's, you know, to sort of figure out what is valuable to estimate. To me, I think estimating some of the things that are otherwise invisible might be of value. But now it gets much more dependent on the particular building and customer, et cetera. And the technical challenges are very different. So we started kind of working on this, you know, like I said, probably 2016, playing around with some ideas. You know, so the first thing we did was we just tried, let's run an open loop model. Let's build a model of a specific building. This is a building, a picture. It's actually next to that high performance building. And it's one of our research labs, and we built a nice model of the 4th floor of that building and calibrated it and ran it open loop. And honestly, this just did not work at all. So, you know, there's some model uncertainty, but you just don't know certain things. A lot of the dynamics are very slow in a big model like this. There's a lot of concrete in this building. So the slowest time constant's like 2 days. And so it takes a long time for things to kind of converge. And we're not really taking advantage of the measurements we have. So, okay, we ran it, but we got a little bit of data. And the second time we thought, well, let's try and design some feedback. Let's design an extended Kalman filter. I'll be smart. I'm a control engineer. I know how to do that. So about this time, you know, FMU was getting pretty mature, and we built that same model, and we saved it as a functional mock-up unit and figured out how to kind of instantiate it and edit it in order to wrap a filter around it. I would say that was also pretty naive. We kind of got it to work. We got it to work well enough to write a paper, and so, you know, that's success to some of us. It was okay. We got to write a paper, go to one of the Modelica conferences. But what failed is what was more interesting. And what failed is, you know, in all of these sort of estimators, you have some kind of, you know, it's data assimilation. So the model predicts something and then you correct it, right? And you're correcting a state. And when you correct the state, there's no reason in the naive approach to think that that correction is going to satisfy your dynamics. And so it also turns out that a lot of these models run very close to their boundaries. Like, you know, the humidity gets very close to 100%, and then the state correction makes it 101%, and then, you know, the model says what, and the solver crashes. So, you know, the Modelica models were not designed for this. They're not designed to change the state in the middle of a simulation. So if you're careful, you can kind of get this to work, but this was a very naive approach. And so then, okay, we got smart, and we thought, all right, now let me skip this one. I put it out of order. Well, never mind. Third one. So our sort of third attempt, which is more recent, is to, okay, now let's be smarter about our constrained estimation, and, you know, make sure that we're not causing state violations. And we used a different platform because it's kind of nice to have the symbolic Jacobian, so thank you very much. Actually could get this to run and predict charge, and, you know, it's a sort of a good first step. And so we wrote another paper, which is great. But, you know, I guess the point I'd like to make is we are so far from sort of really figuring this out, I think. We figured out how to design controllers for this equipment and what the challenges are, but I don't think we've really figured out how to use feedback properly for this type of application. There's no doubt that, you know, I think, in my opinion, that a digital twin at its heart is some kind of estimation. But how do we use feedback to make that robust? And how do we use it with our models so we don't sort of cause bad things to happen? These models are very stiff, as everybody knows. I've already said that. And, you know, really, the estimation theory is not designed so well for those. Especially, you know, if you sort of study extended Kalman filters, the stiffness together with the nonlinearity can kind of conspire together to cause these things to well, I mean, the word is diverge, but I mean, the thing just, you know, it crashes, it doesn't work. So I think there needs to be a better formulation from the very beginning about what this needs to be. So I will say, you know, a sort of equal, in some sense, similar problem is how do you calibrate these models? And there are a lot of parameters in these models, especially for buildings, but, you know, for our equipment too. There are a lot of parameters. These parameters are not necessarily that well known. And so how do we automate the process of building calibration? I do think that these Bayesian optimization methods are very promising. I've spent enough of my time trying to calibrate large numbers of parameters, and, you know, a lot of methods don't really work very well, so you have to kind of break it down to smaller problems. But this seems to be very promising. It's something that we continue to research. I think it needs a lot more research. How to use, you know, Bayesian methods, which are very popular right now, to calibrate parameters, and especially parameters that might be fixed or slowly varying. Those are the ones that are interesting, right? Because over time, the building changes. The emissivity of the building changes. The heat exchanger, heat coefficients change. And those are the interesting pieces of information that we would like to extract. So I'm almost done. I think I am done. I think that there are a lot of challenges in this area, and it's a really interesting area for model-based design. It's an area that might play an important role in sustainability, because if you can monitor this stuff, you can catch problems, and a lot of that, of course, needs to be automated. So if I go back to that zero energy building that I told you about earlier, it's just so chock full of information and displays. In fact, it has so many displays that it's surprising. It actually, I think most of the PV on the roof is used for the displays, but everything's visible. And if you make it visible, then you will monitor it and fix it. And so we need to automate that, but we need to, I think, first, just ask the question, what is this for? What is the digital twin for? And, for us, on the equipment side, it is now very clear. We have a digital platform now, and we can build on that. And, the stars have aligned in some sense. Incentives have aligned. At the building level, I think you have to start with that. What's the purpose of this sort of thing? And then technically, this data assimilation or any kind of estimation that involves, corrections of states, I think needs to be thought through, not just as a hack, not just as a, well, I'll do some projection, or I know humidity can't be more than 1, so I'll just never let it be bigger than 1. And you'll get the simulation to run and you'll get an answer. But, it's much, the problem is much deeper than that. And so, we're kind of back now at looking at the mathematical models and trying to figure out how to formulate what an estimator would look like that, so for example, properly estimates refrigerant charge. So I can go into a little bit more detail. What do I mean by that? In our models, the charge, the amount, the mass of refrigerant is not a state. It's computed as a function of other states. And it's computed as, if I may, a nasty function of the other states. It's got all these nonlinearities. So it's an output, and it's not by any means conserved or caused to be invariant in any kind of simulation. So when we do a simulation from a day to a year, the charge can move around. So is that bad? Because it's supposed to stay the same in a simulation. This is an ideal simulation. Or is it good that it's not a state because, look, it could be leaking slowly? These are all sort of open kind of questions. But we're kind of back looking at the mathematics of the model in order to derive, an estimator and estimate the things that need to be estimated. The full state doesn't need to be estimated. That's sort of a brute force approach. We're only interested in a few things. So again, it kind of comes back to, and sort of summarizing, but for us, I think it's very important to be able to connect and view, the model and the problem as both software, because these things are so big. So that's why Modelica is great. It's very organized. For those of us that are organized, I'm not so organized, but those of you know how to use that stuff. And at the same time, mathematically. And that's a real challenge because you can't just write these equations down, and it's the mathematical structure is what is going to produce, I think, the right sort of solutions to some of these harder problems. And I find that very motivating. These are really hard problems, and I hope some of you also are interested in some of these combination of mathematical problems and software problems, because again, one of my goals here is kind of align interests and incentives, and that's why I think it's important to come to these conferences, right? See people face to face, which is a real pleasure today. So I think I'll stop. I don't think I have any more slides. So, oh, I do have more. I think I already sort of summarized this. I will say this. So we're in Boston, Cambridge technically, the other Cambridge, the one in Boston, just north of MIT for now. Hopefully we stay there. And if anybody's ever in Boston, you are more than welcome to just say, I'm a Modelican, call Chris, and we'll have you over and give you a tour and everything. I really do enjoy interacting with this community. I'm very happy to be standing in front of you. I wish Dirk was here, honestly, but. Oh. Ah! That's good. Because I didn't want to do this again tomorrow. So I'll stop and ask you if you have any questions or comments.
Thank you.
Okay, so Chris reminds me, if anybody online has a question or comment or complaint, go ahead and post it online, and then Chris will relay that to me.
So I have a question regarding little fins. I mean, for many other industries, I see mostly the use of little fins for predictive maintenance. I mean, I could imagine that charge estimation is a predictive maintenance question.
Absolutely.
But it's only one, and there's so many other ones. And there may be many other ones which are actually very valuable and easier to detect, and not that hard, but still very valuable.
Absolutely.
Where we work with little fins, it's mostly predictive maintenance. And there's loads of areas where the math is not that hard and the value is more immediate. And I'm thinking that at least on the buildings level, it must be similar.
So
on the equipment level, maybe not, and I'm not sure that's why you don't care. But
so I completely agree with you. You're absolutely right. And you know, I think that there's all sorts of value to be had here at different levels, and you know, just gaining any kind of visibility into how things are performing is often very helpful. I mean, you know, Chris and I will go look at data that we collected from some system in Japan, and just looking at the raw data. So I completely agree. For predictive maintenance, of course, my company is interested in not just telling you that, you know, our system's leaking, but also, oh, you're only using half the capacity. Next time when we sell you another one, you know, there's all of that. And of course, the opportunities at the equipment level are more transparent to us. I think at the building level, you know, I'll definitely defer. I think it's a much more varied, right? And you know, clearly the whole ecosystem there is very diverse. And but you know, the general point I think you made is I think that this technology, if we think very broadly, can play an important role in addressing some of the efficiency issues, and we might call them, you know, sustainability issues. And so, you know, more power to you.
And I have one more comment is that problem with FMEs is that they don't have to plug into detector parameters. We have a great platform for that. We can do that.
So obviously for the calibration problem, you know, and this is important. Yeah. Okay.
You mentioned embedded FMEs. How do you think the tools should be controlled that control perspective?
So can you repeat the question?
You briefly mentioned at the very beginning embedded FMEs. How do you think the tools should be controlled?
Okay. That's a really good question. I will say that I don't have a lot of experience using them directly. So my opinion is based on what I see in the promise. What I will tell you is there's an enormous need to be able to automate the generation of code for embedded applications. Okay, you know, there's certain companies that are very entrenched in this area, like the MathWorks. For us in this industry, for us, I'm speaking now for just. Maybe that's the right answer, but you know, the problem we have there is, you know, we can't run these models in any kind of desktop or really sort of hardware in the loop simulation with that technology. Just right. So I see EFMI as a way forward, at least for us, and I think by induction similar industries. You know, I'll say one more thing, and that is I've learned something. You know, code complexity inside one tool has just exploded. You know, all these tools are very, very complicated. I can't hardly use them anymore. But when you have 14 or 15 different tools that you're trying to integrate, it's a nightmare. And we used to have to probably translate an algorithm to 4 or 5 different languages before it got into product, all manual. It's a nightmare. So I'm very much in the mind of simplifying and reducing the number of kind of tools and translations that we can do. And so I think that is an important, very important technology. It's never going to be just push the button, you know. But if you organize the controller structure properly into modules and then generate pieces of it, that would save us an enormous amount of effort. When I say us, I mean the company. And it's a big problem. It's definitely a bottleneck. So, you know,
I can say for everybody here, I will tomorrow use the slot about Modelica application to talk about the EFMI standard, the latest Modelica standard. It is not even completely finished in version 1.0 in all of the European projects, but I think I can give an overview, give you a start. I think the tools will be there. It will take time. It's not, I mean, FMI was comparatively much simpler standard. And until that is really used in industry, I think we'll see another 10 years go by also. But I think it's very fun.
yeah, and you know, the opportunity now is to get in early, help shape what that standard is. And I think that's why I think at Mitsubishi Electric, we've got, you know, it's another reason why we've got some interest in investing some time in it. So I'm positive, but as Huberta said, everything takes time. You know, it's going to take 5-10 years before we see that. But, you know, jump in.
Other questions?
Great. So thank you.